So what section 6.2, the first part of 6.2, is we're going to now be looking at calculating the volume between two curves, and this calculation is going to be done through cross sections. As we saw in the GeoGebra website demonstration, you can see what we're going to be doing is we're going to take volume by cross sections. So when we try to find the method of finding the area between two curves, we can actually extend this to find the volume of a solid. The idea is going to be extended by taking different shapes and imagine slicing different slicing shapes. For example, if I take a sphere and I slice it, I can actually have a sphere cut into horizontal slabs, and notice each slab is then of a circle. So like I said, once we divide the solid into thin slabs, we can approximate the volume of each slab, add the approximations to form a Riemann sum, and then take the limit to produce an integral for the volume. So some common cross sections we'll be looking at are circles. We also will be looking, let's say, suppose we take a pyramid and we slice it, we'll be looking at right pyramid. And notice these slabs will turn into squares. A right circular cone cut into horizontal slabs. And we also can have a right circular cone cut into vertical slabs. So like I said, suppose we have a solid that's extending along the x-axis and is bound on the left and right respectively. And again, these shapes are going to be perpendicular to the x-axis. So just like with area, you've got to pay attention whether or not this is going to be perpendicular to the x, which means it's going to be a dx problem, or perpendicular to the y, which means it's going to be a dy problem. So we have a closed interval from a to b, and we're going to find the volume of the solid by assuming that its cross-sectional a of x is known at each x of the interval. So in other words, we're going to take it and divide it into different shapes. The volume of the solid can be obtained by integrating the cross-section from one end of the solid to the other. So the way we're going to do this calculation is, so again, we have the solid that's bounded from x equals a to x equals b in the closed interval from a to b. The cross-section, again, is perpendicular to the x-axis. A of x, and the volume of the solid is going to be calculated by, the volume is going to be equal, again, your lower bound is a to b. Again, these are x values. So notice A is going to be the x value furthest on the left, B is your x value furthest on the right. So again, when we set up your integral, we're going to have your definite integral going from A to B. And then A of x, where A of x is the area of the cross section. So we're going to integrate the area of the cross section. So now we also, like I said, instead of just being perpendicular to the x-axis, you may also be perpendicular to the y-axis. So if you have your cross sections that are going to be perpendicular to the y-axis, then you can calculate the volume, again, from C to D, A of y, dy. So again, C and D are your y values. The lower bound is going to be the y value that's on the lowest part. The d is going to be the y value on the upper part. And then A of y, dy. Again, A of y is the area of your cross section. Now remember, just like with the area problems, if you have a dy problem, remember you have to write each equation in the form of x equals when you go to do your integration. So you have to solve for x. So here are some common slices or cross sections that you're going to be dealing with. Again, possible slices, you're going to be looking for A of x where you're perpendicular to the x-axis. This is what I call your dx problem, or A of y, which means you're perpendicular to the y-axis. They have to tell you whether or not it's going to be perpendicular to the x or perpendicular to the y, and this is going to be a dy problem. Now S is going to be your side down. When you're looking at these next formulas, S is your side down. So basically, if you look, for example, at this semicircle, the side down is the diameter of your semicircle. That's the side that's being faced down in the plane. And when you look at some examples, you'll see what, I'll show you what I mean by that in a minute, but the S is your side down. So for example, suppose they tell you that your cross-section are squares, and they have to tell you the shape of the cross-section. Again, we know how to find the area of a square. It's going to be your base times height. So we know that in a square, all four sides are congruent. So to calculate the area of this individual cross-section, it's going to be, area is going to be equal to S times S, or the area is equal to S squared. So that's the formula we use to calculate the area of our cross-section if it's a square. Semicircle. So again, like I mentioned, this is the side down that's down on the plane. So the diameter is the side down. So we know then to find the area of a semicircle, it's going to be 1/2 pi r squared. However, notice in this area formula, it's in terms of the radius. Again, I know the diameter is equal to 2 times the radius. So again, when I go to solve for r, it's going to be d over 2 is equal to r. So when I rewrite this particular formula, it's going to be the area is going to be equal to 1/2 times pi times d over 2 squared. Or my area is going to be 1/8 pi times d squared. Now remember, S is my side down. So in terms of my S formula, it's going to be 1/8 pi S squared. So if your cross-section is a semicircle, this is going to be the area formula we would use to calculate the area of each individual semicircle, and then we would integrate that formula. We also may have an equilateral triangle. Again, I know to calculate the formula of a triangle, it's going to be 1/2 base times height. And again, I know in an equilateral triangle, all three sides are congruent. So again, all three sides are congruent in my triangle. So using my formula again, here's my height. I know this angle is going to be 60 degrees. This would be 30 degrees. So remember, in a 30, 60, 90 triangle, S is actually equal to 2 times the length of the shorter side. So this is going to have to be S over 2. The height then of this particular triangle is going to be square root of 3 times S over 2. So this is S times square root of 3 over 2. So now I know the height of this equilateral triangle. So then the area formula is going to be equal to 1/2. My base of the triangle is S. My height is S times square root of 3 all over 2. Or it's going to be square root of 3 over 4 times S squared. So if your cross-section is an equilateral triangle, then the area formula is going to be square root of 3 over 4 times S squared. If you have a cross-section that is a rectangle, again, I know the area is going to be base times height. So what's going to happen if you have a cross-section that is a rectangle? They're going to have to state in the problem the relationship between the height and the base. A next cross-section that we could have is a right isosceles triangle. And again, it's going to depend on if the leg is the base or the hypotenuse is the base. So the area formulas will be different based upon whether it's going to be the leg that's the base or it's the hypotenuse. So again, a right isosceles triangle, so we mean we're going to have two congruent sides. So again, I still have my area is equal to 1/2 base times height. So again, if my side's down, it's the leg and the base, then it's going to be, my area is going to be 1/2 times S, or 1/2 S squared. And again, they'll tell you whether it's a right isosceles triangle with the leg as the base or the hypotenuse as the base. So if the leg is the base, this is the area formula. If you have a right isosceles triangle with the hypotenuse as the base, again, here's my right triangle. This is the side that's down. Again, this is a 45, 45, 90 triangle. Again, this angle here would be 45, this would be 45. Well, remember the relationship in a 45, 45, 90 triangle with the two legs and the hypotenuse. Then the sides, the opposite the 45-degree angle is going to be the hypotenuse divided by square root 2. So my area formula I know is going to be 1/2 base times height. So again, the base is going to be, area is going to be equal to 1/2 times s over square root 2 times s over square root 2. So when I clean this up, my area is going to be equal to 1/4 times s squared. You may also have a trapezoid. And the area of a trapezoid, remember, is 1/2 times your height times v1 plus v2. They may also give you any shape. And they may actually tell you, they will have to give you the area of the cross section. So one thing you have to remember, if it's a dx problem, when we're talking about our s, and we're talking about the volume between two curves, it's a ds problem. Remember, it's always going to be your top minus bottom for your dx. If it's a dy, s is going to be equal to right minus left. So the same idea when you were dealing with the area problems, top minus bottom, right minus left. So now let's take a look at some examples here. Like I said, they have to tell you the cross section. They have to tell you whether or not it's going to be a dx or a dy. So just like with the other problems, you have to draw the picture if it's not given to you. So here's where an example where you have squares perpendicular to the x-axis. So they want you to find the volume of the solid whose base is the region bounded by the curve y equals secant of x and the x-axis. Again, if it's the x-axis, we know that that's going to be a dx problem. And it's bound from x equals pi over 4 and x equals pi over 3. So the cross sections are perpendicular to the x-axis and they are squares. So right away, we know it's going to be a dx problem. So you want to identify whether or not it's a dx or a dy. And again, it's a perpendicular to the x-axis. It's a dx. Next, you want to write your area formula for the cross sections. So since your cross sections are squares, the area formula is going to be s squared. So now remember, s is going to be equal to your top function minus the bottom function. So you've got to figure out which function's on the top, which one's on the bottom. So if I graph y equals secant of x, now again, we're only bounding it from pi over 4 to pi over 3. So again, if you remember, your secant graph kind of goes like this. And again, it's bound between the x-axis. So this is the region that we're going to calculate the volume for. So what's happening, again, this is a very three-dimensional idea. What we're doing is we're taking this region, and imagine taking these squares and they're all standing up. We're taking all these in this region, and we're slicing all these squares, and we're going to calculate the area of each individual square. So my top minus bottom then, so here's the function that's on the top, which is the secant of x. The bottom is the x-axis. So the function that's on the top, s, is going to be equal to secant of x minus 0, because that's the equation of your x-axis, or just secant of x. So to calculate my volume, it's going to be bound from pi over 4 to pi over 3. Now remember, the area formula is s squared, and that's what you're going to integrate. So you plug in s into this particular formula, which in this case is going to be secant squared of x dx. So when I integrate, again, I know the antiderivative of secant squared of x is going to be tangent of x. And again, I'm going to have to evaluate this from pi over 4 to pi over 3. So I have to find the tangent of pi over 3 minus the tangent of pi over 4. So tangent of pi over 3 is square root 3, tangent of pi over 4 is 1. So like I said, always identify whether it's a dx, dy. Then again, they have to tell you what cross section they're using. Write your area formula down. If the picture's not given, you want to come up with a diagram and figure out what's the functions on the top minus the bottom if it's a dx. So now here's an example where you're dealing with semicircles that are perpendicular to the y-axis. So find the volume of the solid whose base is the region bounded by the curve 1 minus y, x equals 1 minus y squared, and the y-axis. So that means that, again, that's going to be the equation x equals 0. and whose cross sections taken are perpendicular to the y-axis are semicircles. So again, perpendicular to the y-axis means it's going to be a dy. And again, semicircles. So the area, remember, for the area of your semicircle is going to be pi over 8 times s squared. So what we want to do is look at the graph. So x equals 1 minus y squared. It is a parabola opening to the left. And again, you have a translation going to the right one. So again, the region is bounded between the curve x equals y squared and the y-axis. So again, we're trying to calculate the volume bounded in here. So again, what you have to do is you have to find your bounds. So remember, these are your bounds when x is equal to 0. So what you want to do to find your bounds is you want to plug 0 in here for x. So to find your bounds, 0 is going to be equal to 1 minus y squared, or y squared is equal to 1, so y is equal to plus or minus 1. So the bounds are going to be down here at 0, negative 1, and then 0, 1. So because it's a dy, remember, s is going to be equal to right minus left. So in this case, the function that's furthest on the right is your parabola. So that's going to be your 1 minus y squared minus the function that's on the left, which it's bounded by your y-axis. So the equation of your y-axis is 0. So then s is just going to be equal to 1 minus y squared. And that is what you will plug in to your area formula when we go to integrate. So then the volume is going to be equal to, again, my lower bound, again, remember, because it's a dy, these bounds are going to be in terms of y, be negative 1 to 1. Pi over 8 times 1 minus y squared squared dy. So using my constant multiple rule, I can pull that constant of pi over 8 out of my integral. So I have negative 1 to 1. Again, I am going to have to multiply out this 1 minus y squared, so that's going to be a 1 minus 2y squared plus y to the 4th dy. So now I integrate, I'm going to have pi over 8 times the quantity when I integrate y, that's just a 1, minus 2y to the 3rd over 3 plus y to the 5th over 5. And again, I'm going to evaluate this from negative 1 to 1. Watch your constant, leave that in the front, pi over 8 times. Plug in your 1, you have 1 minus 2/3 plus 1/5. Minus, open up a set of parentheses here. We have a negative 1. Again, this negative 1 to the 3rd will be a negative. That's going to be a positive 2/3. And again, you also have a negative 1/5. So when I simplify this, you have pi over 8 times 1 minus negative 1 is going to give me a 2. Negative 2/3 minus 2/3 is a negative 4/3. 1/5 minus a negative 1/5 is going to give me a positive 2/5. And there's your answer. Now, there's another way you could have also done the integration here. Because this region is symmetric over your x-axis, what you could have also done, another way you could have calculated this volume, was you could have used this idea of symmetry. In other words, we know that the volume that's above your x-axis is equal to the volume that's going to be below the x-axis. So one way you could have done this, another way you could have done this, is you could have done the volume, and you could have doubled it from 0 to 1 of pi over 8 times your 1 minus y squared dy. Sometimes that symmetry helps save you some time. So since that lower bound is a 0, remember when you're doing definite integrals, it's always easier when you have a 0 as your lower bound. So either way you could have done that. So you could have also used the idea of symmetry to calculate this volume. So here's another one where we could be using the calculator. These could be calculator or non-calculator problems. So we've got R is the region bounded by the y-axis of y equals x to the third over 1 plus x squared and 4 minus 2x. The region R is the base of a solid. For each solid, it's perpendicular to the x-axis. So what does that tell us? That tells us it's going to be a dx. And the cross-section is an equilateral triangle. So the formula, remember to calculate the area of your cross-section if it's an equilateral triangle, is square root of 3 over 4 times s squared. So the first thing we have to do is we want to look at the sketch. So we know, remember, s, because it's a dx, is going to be top minus bottom. So on my calculator, when I go to my y equals, I'm going to type in the x to the third divided by 1 plus x squared. Under y2 is going to be 4 minus 2x. Now what I like to do when I'm doing these, so I can distinguish clearly which one's on the top and the bottom, I'm going to change my y2 graph to be very bold. So now I'm going to hit graph. I may need to adjust my window. There's my y1. There's my y2. So I'm just going to make my window, expand that y max a little bit. Let's make that y max to maybe at 10. Let's see what that does. So here's the region I'm going to calculate right in there. So I'm just going to do a sketch. So again, I'm going to calculate the volume right in there. So to find my bounds, I am going to have to find the point of intersection. And again, it's a calculator question, so I can find my point of intersection. So I have this 1.48766, 1.0246. So now you can clearly see that the bold line is the function on the top. And remember, that's what I loaded under y2. So the function on the top is my 4 minus 2x. So s is equal to 4 minus 2x. The function that's on the bottom is what I have loaded under y1, which is the x to the third over 1 plus x squared. So that's my s. So remember, I have this under y2. I always like to kind of make a note of that. This is what I have loaded under y1. And again, you can see from the graph, and again, if I expand out my window, I could change this x min to a -2 to verify it. You can see that both of these graphs are passing through the origin. So I know that the lower bound is going to be 0, 0, 0, 0. So to find the area, or the volume, excuse me, the volume is going to be equal to square root of 3 over 4. I'm just going to pull that out of my integral. Again, my lower bound 0. My upper bound, because it's a dx, is the x coordinate, the 1.48766. And it's s squared. So it's going to be 4 minus 2x minus x to the third over 1 plus x squared. And that quantity is going to be squared, and that's a dx. So just be careful when you, that's why having these functions loaded under y1 and y2 will make sure you don't make a parenthesis error when you type this in. So then on my home screen, I'll go to my alpha window. My integral, again, I'm going from 0 to 1.48766. When you're dealing with these bounds, it's always a good idea to take these upper and lower bounds out to at least 4 or 5 decimal places. Again, I'm going to open up a set of parentheses. Remember, I have 4 minus 2x loaded under y2. So I'm going to be, again, this first set of parentheses is just telling the calculator what functions you're integrating. So you want to open up another set of parentheses, and you want to go to alpha trace y2 minus alpha trace y1. Close your parenthesis, and you want to square it, dx. And then remember, you have to multiply this by the square root of 3 over 4. So with 3.896.